Imagine running against a strong wind. You can feel the resistance pushing against you, making every step harder. This force that you feel pushing you back is known as drag force. It's a type of friction that acts against the direction you're moving. Drag force always acts opposite to the direction of motion, trying to slow you down. Any object moving through a fluid, whether it's air or water, will experience drag force. This includes airplanes flying through the sky, fish swimming in the ocean, and cars driving through rain. As the speed of the object increases, the drag force also increases. This is why you feel more resistance when you run faster or when a car speeds up. Think of putting your hand out of a car window while the car is moving. The faster the car goes, the stronger the force you feel against your hand. This is a simple way to understand how drag force works. The faster the car, the more intense the force pushing against your hand. The shape of an object also plays a crucial role in determining the amount of drag it experiences. A streamlined shape, like that of a fish or an aerodynamic car, reduces drag significantly. A streamlined shape allows the object to move more efficiently through the fluid, experiencing less resistance. This is why fish and birds have evolved to have such shapes. Moving through water creates more drag than moving through air because water is denser than air. This is why swimmers and boats face more resistance compared to objects moving through the air. The density of the fluid is a key factor in determining the amount of drag force. Water, being denser than air, creates more drag on objects moving through it. Understanding drag force is essential in many fields, from aviation to automotive design. It helps engineers design more efficient airplanes, cars, and even understand natural phenomena. By studying drag force, we can better understand how airplanes fly smoothly, how pollen disperses in the air, and how to design objects that move more efficiently through fluids. Scientists use an equation to calculate drag force. This equation is fundamental in understanding how objects move through different fluids, whether it's air, water, or any other medium. By analyzing drag force, scientists can predict and optimize the performance of various objects, from vehicles to sports equipment. This equation considers various factors that influence drag. These factors include the shape of the object, the density of the fluid, the velocity at which the object is moving, and the surface area of the object facing the fluid. Each of these elements plays a crucial role in determining the overall drag force experienced by the object. The equation is drag force equals 1/2 times drag coefficient times density of fluid times velocity squared times area. This formula encapsulates the complex interplay between these factors, providing a comprehensive way to calculate drag force. Let's break down each part of this equation. Understanding each component individually helps in grasping the overall concept of drag force and how it affects the movement of objects through fluids.
The drag coefficient represents the object's shape and how smoothly it moves through the fluid. A lower drag coefficient indicates a more aerodynamic shape, which reduces resistance and allows the object to move more efficiently. A streamlined object has a lower drag coefficient. This is why designs like streamlined cars, airplanes, and even fish are optimized to minimize drag and enhance performance. The density of the fluid, like air or water, is also important. The denser the fluid, the more resistance it offers to the moving object, thereby increasing the drag force. Denser fluids create more drag. For instance, moving through water, which is denser than air, results in higher drag compared to moving through air. Velocity is the speed of the object. The faster the object moves, the greater the drag force it encounters. As velocity increases, drag increases exponentially. This means that doubling the speed of an object results in a 4-fold increase in drag force, making it a critical factor in high-speed applications. Finally, the area refers to the surface area of the object facing the fluid. A larger surface area increases the drag force as there is more area for the fluid to exert resistance on. A larger area creates more drag. This is why objects like parachutes, which are designed to maximize drag, have large surface areas. Understanding this equation helps engineers design more efficient vehicles and athletes optimize their performance. By minimizing drag, they can achieve higher speeds and better energy efficiency, leading to advancements in technology and sports.
In the world of sports, every fraction of a second counts. Athletes are constantly looking for ways to reduce drag and gain an edge.
Swimmers wear special suits to reduce drag. This helps them move faster through the water. Cyclists use aerodynamic helmets and bikes. This reduces air resistance. Even runners benefit from streamlined clothing. It minimizes drag and allows for greater speed. One of the most common examples is the golf ball. The dimples on a golf ball reduce drag. This allows the ball to travel farther. By understanding drag, athletes can improve their performance and break records.
Car manufacturers put a lot of effort into designing fuel-efficient vehicles. One key factor is reducing drag. Cars with aerodynamic designs experience less air resistance. This means they need less fuel to maintain speed. The process involves extensive research and testing, often using advanced computer simulations and wind tunnels to perfect the shape and features of the car.
The shape of the car, from the front grille, which is designed to cut through the air efficiently, to the rear spoiler, which helps manage airflow and reduce turbulence, plays a role. Even small details like side mirrors, which are often designed to minimize drag, can affect drag. By minimizing drag, engineers improve fuel efficiency. Trucks also benefit from aerodynamic designs. Reducing drag is crucial for large vehicles. It leads to significant fuel savings. In today's world, where fuel efficiency is a major concern, these improvements are not just about saving money, but also about reducing environmental impact. Aerodynamic designs help in lowering carbon emissions, making vehicles more eco-friendly. Understanding drag is more important than ever. Engineers and scientists continuously work on innovative solutions to make vehicles more efficient. This ongoing effort is vital for the future of transportation, ensuring that we can travel farther on less fuel and with a smaller carbon footprint.
Section 5. Terminal velocity reaching top speed while falling. You might think objects fall faster and faster forever, but there's a limit. It's called terminal velocity. As an object falls, gravity pulls it down. At the same time, drag force pushes upward. As the object falls faster, drag increases. Eventually, drag force equals the force of gravity. When this happens, the object stops accelerating. It reaches a constant speed. This is terminal velocity. Terminal velocity depends on several factors. These include the object's shape, size, and the density of the fluid it's falling through. Section 6. Skydiving and terminal velocity. A thrilling example. Skydiving provides a thrilling example of terminal velocity in action. As a skydiver jumps out of a plane, they accelerate towards the ground. Initially, gravity dominates and their speed increases rapidly. However, as the skydiver falls faster, air resistance builds up. This drag force opposes the downward pull of gravity. Eventually, the drag force equals the force of gravity. The skydiver then stops accelerating and reaches terminal velocity.
Skydivers can change their body position to manipulate drag. Spreading out their arms and legs increases surface area, increasing drag and reducing terminal velocity.
Section 7. Stokes' Law. Drag for the little guys. Stokes' Law describes drag for small objects moving slowly through a fluid.
This law is different from the drag equation we discussed earlier.
Stokes' Law applies to objects like dust particles, water droplets, and microorganisms. It states that drag force is directly proportional to the object's velocity.
This means if you double the velocity, you double the drag force.
Stokes' Law helps us understand how small particles settle in fluids and how microorganisms move through their environment.
Section 8. Drag and evolution. Nature's streamlined designs. Nature has been dealing with drag for millions of years. Over time, evolution has favored designs that minimize drag.
This is especially true for animals that live in water or fly.
Fish have streamlined bodies that reduce drag. This allows them to swim efficiently. Birds have wings shaped to minimize drag and maximize lift.
Even the shape of a penguin's body helps it move easily through water.
Nature's designs are a testament to the importance of minimizing drag. These designs have inspired engineers to create more efficient vehicles and structures.
Section 9. The importance of drag. From everyday life to cutting-edge technology, understanding drag is crucial in many fields.
In everyday life, it helps us understand why we need to pump up our bike tires to reduce rolling resistance. It explains why we use an umbrella to avoid getting soaked in the rain.
Drag plays a vital role in transportation. Engineers consider drag when designing cars, airplanes, and ships. Minimizing drag improves fuel efficiency and speed.
In medicine, understanding drag helps design medical devices like catheters and stents.
Section 10. Conclusion. Drag, a force to be reckoned with. Drag is a fundamental force that affects many aspects of our world, influencing both natural and man-made environments.
From the movement of tiny particles to the flight of airplanes, drag is a constant presence in our daily lives.
Understanding drag helps us design better vehicles, improve athletic performance, and appreciate the wonders of nature around us.
As we continue to explore and innovate, our understanding of drag will only become more important for future advancements.